This little segment is going to concentrate on types of data. Now, we use numbers very heavily in this course. We're going to be using them all the time, and it allows us to use the computer. Of course, we want to use the computer because the computer is fabulous in terms of doing all the hard work, like the arithmetic, the computing, the storage. It recalls everything perfectly well. Graphics, it does everything. Computers don't make the mistakes. We make the mistakes, and we therefore like to use the computer. Now, numbers have wonderful properties, and sometimes we don't need all the properties every time. So, for example, one kind of data is what we call nominal data. Now, nominal data, let me just give you an example. So, nominal data might be, for example, when we label males as 0, females as 1. That's nominal. Another example is if we use 0 to denote who's alive and 1 for denoting people who are dead. So here, note, it's nominally a number, so just 0, 1. The only property we're making of this number system here is that 0 is different from 1. That's the only property we're making. We're not saying 1 is bigger than 0. We're not saying that 1 is 1 unit away from 0, etc. So this is the simplest example we have of nominal data. In fact, this is sometimes called binary data or dichotomous data. Depending upon whether you prefer the Greek or the Latin root for 2. But it doesn't just have to have 2 values. For example, if we're looking at blood groups, here we would need 4 values. So here we go. If we denote blood group A by a 1, B by a 2, etc., then it's just the fact that these are different. That's it. Okay? It's not that B is bigger than A and AB is bigger than B or anything like that. We're just using the fact that they are different. Now, if you go to FHS.dta, the data set from the Framingham Heart Study that Lauren spoke to you about, then you can take a look and see how many nominal data there are in that data set. So, in summary, nominally, these are nominally numbers. Only in name are they numbers. There's no order. The magnitude is unimportant. So that's nominal data. Now, as we go up the ladder of complexity and properties of data, the next one up is ordinal data. And now, what we want is the order to be important. So here we might classify some disease as mild, moderate, or severe. So instead of mild, we give it a 1. Instead of moderate, we give it a 2. And instead of severe, we give it a 3. Now, here we're using the order of the data. That's why it's called ordinal data. We use the order of the data because 2 is a little bit more severe than 1, and 3 is a little bit more severe than 2. So the order is important, and this is called ordinal data. Here's another example. In the Eastern Cooperative Oncology Group, which is a clinical trials group in cancer, they have come up with this 5-level classification of the performance status of an individual, and it ranges from 0, where the patient is fully active, to 4, where the patient is disabled, and there's a progressive. It progressively gets worse as you go down the scale. So here, the order is important. So this is a little bit more structured than we had with the nominal data. So in summary, the ordinal data, the order is important. But the magnitude is unimportant. We're not saying here that the distance from 1 to 2 is the same as the distance from 3 to 4. The magnitude is not important. Let me clean that up for you. So saying the magnitude from 0 to 1, we take one step, but from 2 to 3, we take one step also. The magnitude is not important. It's just that the order is important. So the order is important, and the magnitude is not important. Now, there's a special case of ordinal data that we use repeatedly, and that is called rank data. Rank data is sort of like when we just had the Olympics. The person who finishes first gets the gold medal, the person who finishes second gets the silver. It doesn't matter how far behind the second is from the first. It's just that the second one finished second. So it could be a fraction of a second to finish second, later than the first, or it could be a few minutes. It doesn't matter. It's just the rank in which the data are ordered. So here, for example, are the 10 leading causes of death in the US for 2010. And we look and see that rank 1, or the highest, or the most deaths in this classification system were due to what was classified as heart disease. Number 2 was cancer. Number 3 was chronic lower respiratory disease, and so on. The numbers, we use the numbers only to order the data. So this is called rank data, and so what we're going to do sometimes is just work as if we had just these data, and forget the numbers, just work with the ranks. And it's amazing how much information just the ranks have and how useful this is. So this is rank data. Sometimes the number actually confuses matters. So for example, if we look at the 10 leading causes of death in 1993, then the numbers are not at the same base level because there were more people in 2000 than there were in 1993. Maybe there were more deaths in 1993. We don't know. But there are the 10 leading causes of death in 1993. And when we compare 1993 and 2010, we see that the first two have remained the same. Stroke and chronic lower respiratory diseases have switched place. This one has remained the same, the unintentional injuries. And now, all of a sudden, in 1993, we had HIV infection in the top 10, and we had homicide and legal intervention in the top 10, and neither of them have made the top 10 in 2010. So presumably, there's been some improvement in those two causes of death. But anyway, the point is, we can't compare the numbers because the numbers are referred to different bases, different group of people. But we can refer to the ranks, and we can make a comparison between the causes of death, where they rank, and so on. Okay, so that's rank data, which is a special case of ordinal data. The next level up is discrete data, sometimes called integer data or count data, because that's what it is. Discrete data is really, well, in mathematics we say you can put it into one-to-one correspondence with the integers, and basically counting. So for example, here are the number of deaths in millions in the world. So this we get from the WHO, and we see there were 7.2 million deaths from ischemic heart disease and 5.7 million from cerebrovascular disease, and so on. So this panel here in the top left-hand corner, this panel up here gives us the world. Now what they did at the WHO, the World Health Organization, they classified each country into one of three groups. Either the low income group, that's this one up here, or the middle income group, that's this one here, or the high income group, and that's this one here. And they base that on the average income per person in the country. So if that's less than $825, then that country is classified as a low-income country. And if it's more than $10,066, that's classified as a high-income country. And in between those two would be the middle-income countries. And you can see that as we change in terms of richness, then the causes of death, as far as the numbers of people are concerned, change. If we worried about the size, we can standardize this and just look at the percent. So this column here, this last column here, gives us the percent, and then it makes sense to compare the different countries. And we're now, this is something we'll talk about later, namely standardization. Now the comparisons make more sense because we are dividing by the population size. So we won't have the population size to be concerned about. Now we can look at these numbers, and this one here, the top left-hand corner, the world, is actually an average of the other three, and we'll talk about averages soon. And what the average tells us is, in some sense, should be the arithmetic average of these three panels. But it's not that, and it's a little bit more subtle than that, and it's actually a weighted average, but we'll get to that later. But from this you can see that, for example, that the number one over here, ischemic heart disease, it's not a 1 here, and it's not a 1 here, it's number 2 here, but it's a 1 here. So somehow what's happening in the high income countries influences what happens in as the overall for the world average. So averages are fascinating things to deal with, and we'll attack that shortly. The last category is continuous data. And this is what we always think of as numbers. We think of between any two bounds, for example, any value is theoretically achievable. So for example, if you think of time, time is one that we typically think we can measure to any accuracy we want, and that makes it a continuous, or length, or mass, or temperature, etc. All of these are examples of continuous data. Now, we can get philosophical here and argue that all measurements, and that's what we're really interested in, is what can we measure, and all measurements are really discrete. All measurements are really discrete. But there's an advantage to modeling them as continuous. And especially if we're going to use digital computers, which we do and will, etc. Digital computers, as the name implies, only handle discrete numbers. Doesn't handle continuous numbers, although they modeled as continuous numbers. But really, there's only a finite number of numbers in a computer, and there's the largest number. We can talk about the largest number, we can talk about the smallest number, etc. Okay, so in summary, these are the kinds of data that we looked at. So this is our taxonomy. It's basically into 4 groups: nominal data, ordinal data, discrete data, and continuous data. And the reason why we go into this much detail is because we are going to use different statistical methods when we have nominal data than we do when we have ordinal data, than we do when we have discrete data, and then we do when we have continuous data.